Hi, I'm Jannis Born from ETH Zurich and IBM Research in Zurich. Today I would like to talk about PaccMann. PaccMann is our project about anti-cancer drug modeling with deep learning methods. And this talk is called PaccMann RL because here we try to design new potential anti-cancer drugs with reinforcement learning directly from transcriptomic data. So we're operating in the realm of drug discovery, which is extremely challenging for several reasons. One is the sheer size of the chemical space, which is estimated to contain 10 to the 30 to 10 to the 60 potential drug-like molecules. And the success rate of all those molecules that are synthesized and tested in the field of drug discovery is extremely low, with only about 0.1% actually reaching market approval at some point. So this has led to increased cost over the last few decades, where this phenomenon is now called Eroom's law, where Eroom is Moore reversed basically, but those costs are doubling about every 9 years ever since the 1990s, and now they have reached up to 2 to 3 billion USD per new FDA approved drug. So basically the problem we are left with is how to meaningfully navigate this huge chemical space in order to reach manifolds that are more densely populated with molecules that exhibit certain chemical or biochemical properties. And the current approaches on how to design new drugs is basically by identifying potential protein targets and then finding molecules that bind to those protein targets and then cause some downstream signal cascade that at some point, for example, causes an apoptotic processes. However, there was a recent paper in Science Translational Medicine which questioned these lead compound discovery approaches. And the title of the paper is Off-Target Toxicity is a Common Mechanism of Action of Cancer Drugs Undergoing Clinical Trials. And here you have to consider that the success rate of cancer drugs in clinical trials is extremely low, only about 3%, although they're already tested with humans. And what they do here is they take 10 anti-cancer drugs from clinical trials, and they selectively knock out with CRISPR the suspected protein target. And then they make two extremely striking observations. The first one being that in all those 10 cases, the cancer fitness of the cells is actually not impaired, although the suspected target is not knocked out. The second observation is that when they now administer the drugs, they actually see that the drugs are equally effective, which means they operate under some mechanism of action which is different to the one that was suspected. And this means basically drugs may not do what we think they do, and for this reason we focus in our work not on protein-driven drug generation, but instead we try to bridge systems biology and drug discovery by generating drugs directly from omics profiles, in our case transcriptomic profiles. So here we have an overview about our framework, which consists of an agent. This is a conditional generative model consisting of two variational autoencoders. The first one is trained on omics profiles from TCGA, and the second one is trained on molecules, bioactive compounds from Campbell, about 2 million in total. And what we can do with this hybrid VAE, we can use the encoder of the profile VAE in order to encode an omics profile of interest, and then we can decode it here with this molecular decoder in order to generate some compound, where this variational constraint in the bottleneck layer here ensures that this decoder will actually generate something meaningful. Initially it will be a more or less random compound, but it will be some compound that can be evaluated here with this predictive model. This predictive model is a drug sensitivity prediction model that consumes a compound alongside an omics profile and predicts the IC50 basically. This IC50 can be interpreted as a reward and used in order to update the generative model, so that this generative model on the long run will come up with more compounds that are predicted to be effective according to the critique here. So for the critique we have a separate paper in Molecular Pharmaceutics. I will not go into the details here. So let's have a briefly have a closer look into how this process works. So we have two VAEs. This one was trained on TCGA. The second one was trained on SMILES from Campbell. And this is an autoregressive decoder here, consisting of recurrent units, where we basically step by step sample those tokens from of those SMILES token here, and we evaluate the reward only once the end token is sampled. So basically once we finish sampling the molecule, we use this predictive model in order to compute the reward that is then used in turn in order to update the generator. So let's have a look at the results. So this is the chemical VAE that was not optimized in this whole pipeline using reinforcement learning, but that was just pre-trained on this Campbell molecules. What we see here is that we have this smoothness in the latent space, where we basically see if we encode ibuprofen and we encode paracetamol and we decode intermediate representations in between of the two, we can see that we can, to some extent, warp or morph one molecule into the other. And this is reached by this smoothness constraint in the latent space that comes from the KL divergence, basically. So now let's have a look into the real results. So here we pick exemplary 3 cancer sites: lung cancer, breast cancer, and autonomic ganglia. And we have 2 distributions shown here. These are IC50 distributions of compounds. So more to the left means lower IC50, so more effective. And the gray distributions are those baseline distributions of the not optimized chemical VAE, where we see that about 2 to 4% of the molecules are actually predicted to be effective, to have a low IC50. And then after the optimization with the deep reinforcement learning, we see that we can shift those distributions. We get those new red distributions here, where we have about 20 to 30% of the molecules that are actually predicted to be effective. So let's have a closer look into how these molecules look like. We have here a bunch of those structures depicted, and we did a comparison analysis to molecules that are known cancer drugs from GDSC or CCLE, those cancer drug sensitivity databases. And the most striking observation we have here is that those molecules that we sample for specific cancer sites have actually the highest similarity to compounds that are known to be effective for those cancer types specifically. So here the nearest neighbor in relative terms, in absolute similarity is not very high, but in relative terms the nearest neighbor is doxorubicin, where doxorubicin is an improved chemotherapeutical that's mostly used against breast cancer. And you have similar observations also here in the case of lung cancer and neuroblastoma. However, there are various other properties that qualify or disqualify a molecule for being a drug. We therefore assess synthesizability and drug likeness of the real and generated anti-cancer compounds, and we show here the kernel PCA of those 2 distributions, and we don't see any obvious dissimilarity in between of the two. The same holds true also for water solubility, although none of these properties was directly optimized. We then used IBM RxN, which is a platform for automated chemical synthesis, in order to assess whether we can also synthesize those compounds. And we see here that for this exemplary compound, we only need a set of 6 reactants, and we only need to perform about 2 reactions in order to obtain and synthesize the molecule of interest. And with this, I would like to close. Thank you for your attention, and I would deeply like to thank the Computational Systems Biology group at IBM Research in Zurich, especially Matteo Manica and Ali Oskoy, and also the Machine Learning and Computational Biology group at ETH in Zurich.